Hello, welcome everyone. It's May 5th, 2025, and we're in Active Inference GuestStream 106.1 with Bang Liu and colleagues discussing an epic work, advances and challenges in foundation agents from brain-inspired intelligence to evolutionary, collaborative, and safe systems. So, thank you to many of the authors for joining, and I will pass to you all to present, and looking forward to hearing about this. Go for it.
Okay, yeah. Thanks, Daniel, for this invitation. Hello, everyone. My name is Bang Liu. I'm an assistant professor at the University of Montreal and a member of DIHO and Institute Courtois of the university, as well as a member of MILA Quebec Institute. So today I'm going to briefly first introduce the concept of foundation agents. So this is a collective work together with many of our co-authors. So here today we have Shaokun, Hongzhang, and Xiaoxiang joined as well. So I will start from this brief introduction about the whole concept and why we do this work. And then our other co-authors will briefly talk about the parts they are more familiar with so that we can went through many parts of the large survey. But of course, we cannot go through every details of that long paper. So if you're interested, feel free to check the original paper and contact us if you have any questions. Yeah, so I will start from the introduction. So as we know that our human beings has long been interested in developing some intelligent things as smart or maybe even smarter than ourselves. So for example, on the left figure, so it is the Talus of Crete, where it shows a bronze automation from Greek mythology built by the harvesters to protect Crete. So basically people want to build huge robots to defend their home. And in the middle, this image shows that Leonardo da Vinci's humanoid robot, which is an early mechanical automation designed to mimic human motion. And on the right part is a figure shows Alan Turing's paper. So the computing machinery and intelligence, which proposing the fundamental question is about can machines think? So we can see that AI has long been driven by humanity's ambition to create entities that mirrors our intelligence. So maybe let's start from the very simple question. What is exactly an AI agent? So if you check a textbook, like the AI textbook, so maybe you will see some definition. So briefly speaking, you will see that agents is something intelligent beings continually perceive, decide, and act autonomously. And in this figure, I think this figure is from the blog of Dr. Weng Lilian. So which shows that how what kind of components composed to form an LLM agent. So traditionally, the agents are mostly rule-based, domain-specific, so it's hard to generalize. But with the development of large language models, so we have developed large language model-powered agents, which has the natural language fluency, the broad reasoning capability, and dynamic adaptivity to different tasks, environments, and so on. So on the right figure, you see that LLM agents composed of one LLM and together with several other components like a memory module, planning, tools, actions, and so on. Of course, this is a very basic setting of LLM agents. And in real world, there are many different agent architectures, which may include much more rich components. So you may think why we conduct such a large scale survey. So we're actually motivated by several questions. The first is we want to know where are we in AI research today. So we have powerful language models, impressive reasoning capabilities, but we still have limitations in AI safety, the controllability of AI models, the reliability of the answers, and the trustworthiness in different high-stake fields. For example, can we safely utilize and trust AI in health domain, in legal domain, and so on? And what can be improved? This is our second question. So by making a comparison with biological intelligence, with a thorough check of the current progress, we want to know what to do next. So in this work, we want to develop a unified framework for AI agents. And based on this framework, we can systematically check the progress and the future. So we emphasize the modularity, the safety of AI, the lifelong learning capabilities, emotion grounding, and so on. And why we want to connect AI with human and society. So we can think that like our human beings are the kind of intelligent things we only know about, right? So we want to draw insights from human brain functions and social behavior and identify the gaps by comparing like human cognition and AI agents and develop human-centered socially beneficial AI and foster human-AI collaboration, transparency, and trustworthiness. So maybe you ask that, like, do we need to actually always mimic human brain to create intelligence? As you can see that nowadays the LM, actually we draw very weak inspiration from neuroscience, right? We have the artificial neurons, but all the others are mostly based on the modern machine learning development, which is less grounded to most advanced neuroscience developments. But there's benefits to compare human brain and LM intelligence because like if we want to develop some trustworthy AI, it's better to make it more close to what we actually knows about. Although that I need to emphasize that it's not necessary to mimic or like clone every capability or feature of human brain, but it's beneficial to have a comparison with. So this is a very brief table that compares human brain and LM agents from some perspectives. Of course, this is not a thorough list. You can check more detailed comparison in the paper. But like, for example, from the hardware level, human brains are composed of biological neurons. It's highly energy efficient. But as we know that LLMs are pre-trained with large-scale GPUs, large-scale datasets, so it's energy intensive. So this is the fundamental difference between the hardware level of human biological intelligence or AI, current AI. And consciousness, so until now, I think maybe it's safe to say that AI is not conscious until now, but for human beings, it's genuine subjective experience, so we can feel that we are conscious. And for learning style, human beings are naturally be able to perform lifelong continuous learning, and we can quickly adapt to different tasks with few shot or one shot learning. And for LM agents or other neural networks or machine learning models, it's more challenging to do that. And human brains is more emotional, experiential, subconscious driven, and LM agents and other machine learning methods is more about statistical data driven recommendations. So one investigation we have conducted is like we want to know for different capabilities of human brains, how is it developed in the current AI technique? So we can grossly classify different types of capability into three levels. Whereas green color L1 denotes like some features which is well developed in the current AI technique. So for example, we can consider that language comprehension is quite advanced nowadays. So if you ask language model different things, it can understand your input text very well. And also for advanced computer vision models, it can also have very strong visual perception capabilities. And L2 is more moderately explored with partial progress. So for example, like maybe you think the logical reasoning capability of LLMs is quite strong, but there are also research paper shows that if you like carefully adjust the format of your input questions, make it different from the training data, like the performance can drop quickly, right? So we can see that the reasoning capability can still, like, there's a large space to improve yet. So we can see for many such capabilities like reasoning, planning, working memories, attention, and so on, there's still large space to improve and explore. And there are also some capabilities which is rarely explored, those pink colors. So we call it L3. So it's rarely explored capabilities. There's significant room for research. So for example, the emotional processing, the self-awareness, empathy, and automatic regulation, and so on. Of course, like in this figure, maybe some of the capabilities kind of between L1 and L2 or L2 and L3 is kind of subjective, but that's not important. What we want to show is that what is like to show a research map of the current AI development and to see what to go next. So one challenge for existing agent research is that we lack a unified framework. So the current AI agents often built in ad hoc, fragmented ways, which means like people construct different agent frameworks by incorporating different parts, components, and there's no unified framework which can be suitable and adapted to different application scenarios. So we lack seamless integration of perception, memory, reasoning, action, and many other modules. But human brains integrate yet modular approach, self-enhancement inspiration. So in our survey paper, we actually proposed a framework. So this is some notations about the framework, but we don't need to remember that. Let's directly check this figure. If you check this figure, like we can see that there is a like the left part is a world where you have different environments, you have users, you have external data, and many other things. So basically, you can consider the environment, there's the environment state space S with state transition function T. And we have an intelligent agent on the right part with the pink colored circle. And it has sensors to perceive the environment, and it has actors to execute actions. So from the high level, it's like similar to the traditional like RL agent framework, right? But here we emphasize more about the internal like states and the learning and reasoning capability. So we want to like clearly modeling what is the perception, cognition, and action components in an agent loop. So here we show some mental states where we have the world model mental state. We have the memory, we have goal, the emotion, reward. So basically we think those are like 5 key mental substates in the mental state of the cognition module. And like based on this mental state, the core capability of cognition is actually the learning and reasoning capability, where we define learning as the capability of like update the mental states based on the input data and past experience. And the reasoning is about, based on the current mental state, decide what kind of actions to take. So we can check this agent loop explanation, which is a more formal way to describe the agent loop, which is equivalent to what we are conveying in this figure. So let's say we have environment state as a time step t, which is st. And we have a perception module. So this perception function p is defined by the actors, right? We have different by the sensors. We have different sensors. So this forms observation O of t based on the state and prior mental state. So here we define the observation at time step t, OT equals to the perception function's output p given the current environmental state as of t and the last mental state t minus 1. And based on the observation, we have the cognition part C. Well, the key functionality of the cognition module is first, update the mental state at time step t, which is m of t, and decides the next action, a of t. And we further decompose this cognition process into 2 key parts, learning and reasoning. Well, learning is about, so you have the mental state based on the last mental state t minus 1 and last action a of t minus 1 and the current observation of t. We're updating the mental state. So basically you can consider that learning is about like update your internal structure, your internal like modeling of the world, right? So basically it's kind of a long-term effect. That's why learning is about maintaining, updating your mental state MT. And we decompose M of t into several big subcomponents like the memories, world model, emotion, reward, and goal, and so on. And for reasoning, it's more about, based on the current context, we decide what we need to do in the next. So that's why reasoning is about, given the mental state of current time step t, mt, we decide what is the action to take, AT. And action execution, so it aims to convert the chosen action into executable forms. So because like you can consider the reasoning output is a thought about what action to take, but to actually execute it, you need to like have strong actors which can execute the action accurately. So for example, consider like you want to control a robot in a 3D environment, right? If your actor is not good enough, maybe it cannot continuously accurately control the actors. And finally, like based on the executed action, so the environment state will transit to the next state, which is ST plus 1. So you can see that the key designs here are two parts. The first is about the definition of the mental state, where we have further divided it into several sub-mental states. The second is about how we like accurately define the perception, cognition, and action, including action execution, as well as environment transition and so on. So we make each part more concrete. And we further define what we call the foundation agents. So in this box, this is the definition we give in the survey paper. And after that, we further consider, okay, can we give it a more like concise definition? So basically, we can say that foundation agent is a fundamental intelligent unit with universal understanding, cognition, and action capabilities that can operate in any environment and collaborate to form collective intelligence. So note that here we actually emphasize on two parts. The first is about the universal capability in different environments. So that's why we call it fundamental, the foundation, because like we want that the agent can be easily adapted to different tasks, different environments. And the second part is about the collaborative capability. So we consider a foundation agent can easily collaborate with many other agents to form a multi-agent system or even an agent society. So the reason is that like a multi-agent system can have advantages in terms of the performance, efficiency, and many others. So even like if you think, can we create an agent as powerful as a god? Maybe this is not the ideal solution. And also, if you consider the performance, the energy consumption, the working efficiency, and so on, so we think a multi-agent paradigm can be a better solution compared to a single agent. That's why we emphasize on the collaborative capability of the foundation agents. So we emphasize on several core capabilities. Well, the multimodal perception is about the perception capability, the cognitive adaptation, and the goal-driven reasoning, the purpose for action, and the multi-agent collaborations. We also like checked and compared to existing other classical theories. So for example, the classical perception, cognition, action cycle. So these are a part of our agent loop as well. And the Minsky Society of Mind. So we have modular cognition subsystems like the memory, emotion, reasoning, and so on. And there's also the theory from Busaki's inside-outside perspective, which emphasizes that we are not passively like accept observations from the environment. Actually, we're actually seeking actions actively. So which emphasizes on the action first perspective. So here we have internal mental states actively shape the perception. And for PMDP framework, here we emphasize the internal mental states and the active learning and reasoning process compared to the PMDP. And for Bayesian active inference, here we minimize the prediction area while updated world models. So until now, I have introduced the definition of the foundation agents and the agent loop. Next, I will quickly run through some like highlights of the agent modules. So for example, like first is the cognitive core, which is the central executive that orchestrates the reasoning, planning, reflection, and many others. So here, if you remember that we define cognition as like have two capabilities, right? The learning and the reasoning. And for reasoning, so in our survey, we investigated different reasoning paradigms, include structured reasoning, Well, actually, the reasoning process is following some structure. For example, the multi-chain or tree structure, or a graph structure, and many others. And there are also unstructured reasoning process. For example, it's more about sequential decision making. It's like in a chain style, or maybe you can also reason in the latent space. So basically, you can transit between the latent space and the token space. And for planning, you can consider planning is a special action where you take the input and you like decide a more long-term plan for different actions, right? So that's it. Like first, planning is a special action, and the second is that it's more about a larger scale of the future actions. And for memories, like the multi-level memory inspired by biology. So we talked about the short-term memory, the working memory, long-term memory, many other types. And so memory can enable continuous learning and while avoid catastrophic forgetting. So the design challenge here is that how we can perform fast query over vast memories with minimal latency and cost. So one highlight in our survey is we formally define the life cycle of memory. So just start from the memory acquisition, where we draw information from the raw observations, and then we turn it into encoded information. And we also drive new memories. For example, you can, let's say if you have a dialogue, you can drive some summaries from the dialogue, or maybe you can also infer some new information which is not explicitly stated in the dialogue history, but it can be inferred with logical inference. And then after the derivation, we have the retrieval and utilization. And both model is an internal representation of the environment's dynamics and the agent's own causal influence. So basically, you can consider what model helps you to predict the future without actually like taking actions in the reality, right? So for example, just like how you do sports, when you like choose your actions, you can predict the result, whether you can hit the ball, well, the ball will fly to other objects and so on. So because you have the model about the world and about the cause effects, so in this case, you can like decide your appropriate action to take without like high cost, right? And here we define the core functions in our world model as the transition function and observation function. What is the transition function is like you have the current world state and you have a new action. Based on the action and the state, you will transit to the next state. And for the observation function is like based on the current state, what kind of observation you will have. So by considering how different model or algorithms define the transition function and observation function, so we categorize different research works about world model into 4 categories, includes the explicit, implicit one, explicit, paradigm, simulator-based, and hybrid or instruction-driven. And for reward and value system, so basically reward is goal signals that shape learning and behavior. So we also discussed different types of reward in our survey paper. So for example, we have extrinsic reward, which is defined by some external reward evaluator, and the intrinsic reward, which is, for example, the agent may perform some self-reflection to decide whether the result is good or not. And of course, there are also hybrid reward, which combines both external ones and internal ones, and there are hierarchical reward, which models more complex context. And I think emotion is actually an interesting topic, which is less explored in the existing AI research. So emotions act as fast heuristics. So you can consider that actually emotion has very close relationship with rewards, right? So like fear helps you to like do some avoidance to avoid some danger, and curiosity will increase your chance to do exploration. So basically, emotions can impact your decision about what actions to take in the next. So it supplies sustained internal drift and also adds robustness and adaptability, but demands tight control to avoid undesirable side effects. So this is one figure we put in the survey paper. So basically, here we show some classical emotion models. There are some categorical emotion models where you can divide emotion into different types, or there are some dimension-based models or hybrid models and so on. Of course, like these are not the full spectrum of emotion models, but they represented like stereotypical categories. And for perception, the key is about how we can deal with multimodal signals and how we can appropriately encode the signal, fuse them, align them, and so like if you check the current human perception capability and agent perception capabilities, they have their own unique perception systems, and they also have a large part which is overlapped. And lastly, like for the action system. So the action system is about how we convert cognitive decisions into executable commands. So actions can be taken in different formats, right? For example, it can be as simple as just a natural language response, or it can be some code to be executed, or robot control in the real world, or virtual navigation. So we need to balance the feasibility, efficiency, and safety. And also we need to learn fine-grained skills and operate in continuous action space. And in this figure, so the purpose is to like clearly differentiate different concepts that may be ambiguous. So for example, like you have a cognition system, right? The cognition system will produce your action source, which is the directive source arising from the cognitive reasoning. And to actually execute this action source, you need to have an action system where it can take the source from the cognition into executable actions. And the action system can call different tools. Well, we define tool as callable utility for specialized execution. And API is a format of the tool. So you can also have other tools which is not in the format of APIs. So we define API as interface for programmatically invoking service. And for functions is the most atomic unit of implementations. So an API may include one or more functions. So I cannot cover all the parts of this law survey. So if you're interested, like feel free to check our survey in this link. And thank you. I will stop sharing here.
Thank you. Will another author like to present or share anything?
Yeah, I think next we can who want to start first, following the order of the survey paper. So
I think next I can introduce our memory chapter for the survey paper.
Awesome.
Can you see my screen?
Yep, go for it.
yes.
Okay, yeah, let's move on. Hello, everyone. I'm Xiaoqian Wang, currently a PhD student at the University of Montreal and the Miller AI Institute, working with Professor Wang Liu. My research lies on the intersection of large language models and autonomous agents, especially how can we give agent human-like memory and reasoning capabilities. Today, I will briefly introduce our chapter on the memory in the survey paper, which I co-authored. Generally speaking, memory is a fundamental component of intelligent agents. It enables the agent to call past experiences using their stored knowledge over time and reasoning effectively. I will go through three parts following the structure of the paper. The first part is a quick overview of human memory and how this later introduce how this concept inspired the representations of agent memory. Then I will introduce how the agent memory goes through a life cycle from storage to use. So the first part is the overview of human memory. In the cognitive psychology, the gives us a framework that breaks down human memory into three core types, includes sensor memory, short-term memory, and long-term memory. For sensor memory, captures immediate or fleeting impressions from the environments, like visual and audio inputs, and holds them for milliseconds to seconds. And in a more longer duration, short-term memory or working memory holds information we are actively using, like the phone number you have just heard, or mathematical maths. It's limited in capability and durations, but essential for reasoning and decision making. And yet, longer duration, long-term memory stores knowledge and abilities across long time, lifelong time, such as personal memories or learned facts. It is more durable and expensive. So for each type of the three kinds of memory serves a distinct role. For intelligent autonomous agents, we mimic these functions and enable much richer and more adaptive behaviors. So in the longer agents, we draw direct inspiration from this human memory and design the agent memory also follows the three kinds of memory, such as sensor memory, short-term memory, and long-term memory. The sensor memory focuses on the raw observations and input logs, and for such as incoming data like user queries, the tool outputs, and the web search paths. These are often stored temporarily as text space or multimodal format. They provide the raw material for further processing, just like how humans take insights and take insights and sound. For the short-term memory part, also known as working memory or content memory, this is to enable the continuity of the task and enable cross-task realization. This includes the information that agents need to right now to complete the task. In practice, this is often handled through a prompt where the agent holds a chain of thought, recent user turns, or scratchpad reading steps. So the short-term memory is also volatile. Once the task is done, much of this memory disappears unless it's explicitly stored or we convert the short-term memory to long-term memory. And for the long-term memory, that means the precision and such as persistent storage is where agents store information across tasks and across sessions. So there are two kinds of subtypes of long-term memory: episodic memory and such as semantic memory. So the episodic memory such as past events, that is past interaction and tool usage, or summary of completed tasks. And this task involves the agent to generalize more unseen tasks and unseen future queries. A semantic memory stores structured knowledge such as the rules, concepts, and the facts that agent has learned or extracted from past experience. Together with the three kinds of memory, the agents can build up its own experience over time, adapt to users and reflect on their own behaviors. So the core part of the memory chapter is the memory life cycle and the heart of agent memory. It is the stage the agent goes through the process and use memory. So in the agent memory cycle, in the agent memory life cycle, we decompose the memory usage into memory retention process, retrieval process, and memory storage. So in detail, there are 7 stages in the memory life cycle. The first one is memory acquisition. The agent observe external signals such as tool responses, environment, state, and then based on the user query, then filter the raw data into the structured data. This is like sensor perception, collecting raw data from the external environment. And the next second stage is the memory encoding. Here, the agents process raw input into structured representation. For example, iterating named entities or task outcomes, and then summarizing the a long dialogue, converting the outputs into a knowledge graph or memory entry story. This is where the meaning or internal meaning from external world is contrasted from perception. And then another core part is the memory derivation. The agent may further derive insights or new knowledge from existing encoded memory, and this process may be iteratively executed to in the lifelong memory derivation. For example, we can deriving task success or failure labels, detecting user preferences, inferring dependencies, or causal relationships. So this helps the agent grow its internal state of external world. Another part of the memory cycle is about the storage of memory. So agent decides where to store in long-term memory and how the memory is stored. The key techniques include which memory to keep versus which memory to discard, such as how to index the existing memory or text them, and how to represent them from label retrieval, such as based on text-based retrieval or embedding-based retrieval from some such as embedding database. This is where capacity, it's more about the capacity management and relevance fitting become it is critical technique to design this part. Another part is about memory retrieval. When solving a new task, the agent retrieve relevant past memories. That might involve such as semantic search or querying by task type and user filtering based on the recency and relevance metrics. So an effective and efficient retrieval ensures memory actually supports more enable more to future decisions. Also, retrieval memory can be integrated into an agent's prompt or reasoning process. It can involve the formatting memories for large amount of input and summarizing retrieved items and injecting context selectively to fit token limits, reading what is connected from the past experience to present actions. Finally, part is how can we update the memory over time, refining entries or removing outdated ones. So the techniques for this part is how can we editing old memories with new info, and how can we forgetting irrelevant data and reinforce frequently use the memory, such as human can actively rehearsal our memory and to strengthen our stored knowledge. So agent memory for this part is dynamic and can be adaptive to more future tasks. So in summary, in the memory cycle, we model the memory in agents by drawing directly from the human cognition and in designing 3 types of memory: sensor memory, short-term memory, and long-term memory. And each memory type has its counterpart in current larger model agents in both richer and more context-aware reasoning or behavior. And we formalize the memory life cycle into the 7 stages, from memory acquisition into memory updating. And this life cycle allows agent to actively perceive its encode and remember and grow over the lifelong deployment. So which is essential for building intelligent and adaptive systems for the foundation agents. So that's all my introduction for the memory cycle. For the memory chapter.
Thank you.
Okay. Now let me introduce optimization and self-involutions part. Hello everyone, and thank you for having us here. My name is Shaokun Zhang. I'm currently a PhD student at the Penn State University, and now I'm interning in Bay Area at NVIDIA Research, and I will be mainly covering these sections. So the main idea of this section is how can LM agents could improve themselves over time without the human's help, and the paper breaks this concept into several parts. And the first part is the optimization space and dimensions. It means that in these sections we give a formally defining of what kind of component in the agentic system could be optimized, and we go through the current research and we summarize it some in this component, like the prompt optimizations and like the prompt optimizations and the workflow optimizations, and as well as tool optimizations. These three parts are the community puts their most efforts on, and we also expect that now we not if we want to optimize an agentic system, we are not only on we do not want to operate them separately. So we in ideal cases we expect we could operate them comprehensively. So we also gave summaries of current efforts in how current research works trying to optimize agentic systems in their multiple aspects, like the prompts, like tools. So this somehow like a multi-objective optimizations. And in the next chapters, we are mainly discussing the using large language model as an optimizer. So if we want the agentic system could get a kind of involutions, we may expect that we may not use directly using the traditional optimizers to optimize this agentic system, because traditional optimizers are mostly gradient based. So large language models are now should be the engine for conduct this kind of optimizations. So in this chapter, we first gave a brief overview of traditional optimizers and discussing why it can works in our scenarios. And then we discussing the current approaches for using LLMs as optimizers to optimizing different objectives, and the most important part is agentic systems and LLM systems. We discuss this in these subsections. And next, we discussing when using LLMs as optimizers, we discussing the hyperparameters of when conducting such a kind of optimizations, because we observe that when using LLM as optimizers, the hyperparameters plays a critical role, and it will greatly define how the LLM performs when conducting the optimization functionalities. We discussing the current efforts of exploring different hyperparameters when using LLMs as optimizer. And then in the next, we discussing the optimizations across dips and time, which we mainly discuss the scope of when performing such a kind of LLM optimizations. We also do a theoretical discussion of current efforts in discussing why LLM could be regarded as optimizers, and we make a survey of current efforts in summarizing this theoretical papers. Next, we are mainly discussing the application scenarios of when performing the agentic self-involutions. We we categorize them into two cases: the online self-improvement and the offline self-improvement. For online self-improvement, it is the most ideal cases that, okay, now we have agentic systems. When we deploy it in a specific applications, we may expect that it could, just like human beings, to learn from past experience and learn from failures and get involved themselves. Optimizing its prompts, optimization its tools, and optimizing its workflows. Even optimizing the agent different roles in a specific agentic systems. And this is the most ideal cases, but it is also more hard than offline optimizations. But so we discuss the current efforts in building online agentic building agentic systems that could online to self-improve themselves. This is the first subsections we discuss in this chapter. And the next is offline agentic self-improvement. Compared to online self-improvement, offline self-improvement means that, okay, now we have agentic systems, and we also have curated data, and we, before deploying these agentic systems in realistic, we first to optimize these agentic systems using the curated data and ensure that it could work well on this kind of training data, and then we make the deployment. And this is the most common accepted practice in building up the agentic system, because it's more simple and also has been demonstrated is more effective. And the most efforts are putting up here, but it is not ideal enough. We also make a comparison between online and offline self-improvement to summarize their different features and their what in common and what not in common. And finally, we also discuss current efforts in the hybrid approach. We combine both online and offline. We first using the curated data to build up a agentic system to ensure it has a great foundations, and then we also add some online learning algorithms when deploying it in practical, and to ensure that it could work well and learning from past failures. So this there are also several works focusing on this perspective, focusing on this pipeline. And in the last chapter, we are discussing the scientific discovery and intelligent evolutions, because in this section, in this part, we mainly discussing the self-evolutions. So for self-evolution, we mean that it could improve themselves without the humans' help. And the new knowledge discovery means that, okay, we have a training set, we build up agentic systems. If the agentic system could discover some new knowledge that human beings do not know, and which means this knowledge didn't include it in their training set. So this could be regarded as a kind of self-evolutions, and this is very important. We expect somehow in the future, we may expect the agentic system could learn from themselves and doing their own research. So this is a kind of self-evolutions, and we discussing the current efforts in using agentic systems in scientific discovery and in perform scientific experiments. And we put a lot of efforts in summary these sections. And yeah, that is what I want to share today.
Thank you.
Thank you.
Okay. Hey. Hi everyone. My name is Fengzhang Liu, and in the third part, I'd like to take you beyond the individual agents to explore how they work together in what we call multi-agent systems, or MAS for short. Yeah. And our paper expand beyond single agents to examine these systems composed with the multiple foundation agents. We discuss their components, their structures, and how they cooperate, and their decision-making mechanisms. We also explore the emergence of collective intelligence when these agents collaborate or complete autonomously. And by the end, we will review the evaluation methods that help us understand and measure this complex system. And okay, let's begin with the first chapter, the multi-agent system design. When we build LLM-based multi-agent systems, what's the foundation? We suppose it's for the cooperative goals and norms. These are significant because they shape everything else. The system's constraints, how agents interact with each other, and the overall mechanisms for working together. And think about this way: collaborative goals tell each agent what they are aiming for. Whether that individual success, collective achievements, or competitive advantage. Meanwhile, the collaborative norms are like the rulebook, and they establish how agents should interact and what constraints exist and what the convention to follow. Based on these foundations, we can organize the multi-agent systems into three main types. Those focusing like the strategy learning, like the design for the modeling or simulation, or those beautiful some collaborative problem solving or task solving. Yeah, and in our paper we analyzed the typical applications across these three categories to understand how LLMs are transforming agent behavior and interaction and agent decision making, and which leads us to suppose the next generation agent protocols that specifically designed for LLM-MAS system. Yeah, and we also discussed the collaborations patterns because like humans have the diverse ways of interacting. We build like the concepts, learning skills from each other, or divided task by ourselves. So our research examines multi-agent collaborations through three dimensions. That's purpose of like the interaction, like the message type, this form, and the relationship involved. Yeah, and depending on their goals and forms, they may be like the discussions or the debates form or the voting, or create each other in one ways or multi directions interactions. Yeah, and I think the next chapter is one of the most significant, and which is the combination topologic, or you can think it is the multi-agent systems topologic. From a system perspective, the topologic or the connection pattern often determine how efficiently agents can collaborate or what their upper limits might be. Yeah, we classified multi-agent system topologics into two major class. The first one is the static topologics. It may include the hierarchical and centralized structure or the decentralized structures. For example, and these are typically used when solving specific task. Like our MetaGPT, we use SLP to predefine this workflow of the software development cases. And the other class is the dynamic and adaptive topologics. It can be achieved by emerging algorithms like the search-based and the the generative based or the parametric approaches. And when we look to the future, scalability becomes a crucial interest. And how can we do for efficiently scale this system as the number of agents increases? This is one of the key challenges in the future research we need to address. And we suppose the collective intelligence and emergencies in MAS is an important tool because it doesn't just appear, it develops by a dynamic and iterative process. Through the continuous interaction, agents greatly build shared understanding and collective memory. And what drives this process? It may be the diversities of the individual agents, feedback from the environment, and how information gets exchanged between agents. And these factors create dynamic interactions that's crucial for forming complex social networks and improving decisions strategy, which leads the emergent behavior phenomena like trust and strategy description and so on. We call this like the self-evolution, and it can happen through memory-based learning or Patrick-based learning. Yeah, and in the future, we hope that what is even more fascinating is that as the system evolved, agents begin to form social contracts or like organizations hierarchies and the division of labor. It's just like the human societies. Yeah, thus understanding this phenomenon represents one of the most exciting directions of the future MAS research. And the last in the last part, we summarize some multi-agent systems benchmark. Yeah, as the multi-agent system demonstrate more advantage, so we need to fundamentally transform how we evaluate them. MAS evaluation should focus on holistic nature of the agent interactions, not just in individual performance. Key dimensions include how efficient agents can plan together, and the quality of the information they exchange, and how well they make decisions collectively. Yeah, and in our paper, we summarized the two approaches of the evaluation, like the task-solving benchmarks and the generative and the general capability assessment. The first may be focused on measuring how deeply and currently agents coordinate decision across types of environments. The second evaluates how well groups of agents interact and adapt within complex and dynamic scenarios. These evaluation frameworks give us the tools to understand and measure to improve multi-agent systems for the future applications. And that's all of the something important of the part. And that's all. Thank you.
Thank you.
Okay, let me share my screen.
Very exciting. I think it's the most presentations we've ever seen back to back, but appropriate for the multi-agent theme.
Thank you.
Can you see my screen?
Yeah.
Not yet.
Yep.
Okay. Okay. Sorry, my camera seems to be broken, so let me start this part. Hello, everyone. My name is Haibo Jing. Currently, I'm a PhD student at University of Illinois at Urbana-Champaign. Today, I'm going to talk high-level introduction about building safe and beneficial AI agents. As we all know, as we all know, the rapid development of large language model-based agents introduce a new set of safety challenges. We categorize these safety challenges into intrinsic safety and extrinsic safety. We use a figure to illustrate this problem, and for the intrinsic safety, we divided them into 3 parts. The first part is perception, and the perception part is the large language model based agent can see the world, and the brain mainly talk about the large language model itself. It include a large language model to extract the data, decision making, and the action part is how this large language model can act. And for the extrinsic part, we divided them into environment, memory, and agent interactions. So the overall pipeline of this part can be seen in figure 17.1. And for the first part, the intrinsic safety, we mainly talk about the threats on AI brain, which is large language model itself. We divide them into 5 vulnerabilities. The first of all is jailbreak attack. As we can see from this figure, normally the malicious attack will send the malicious attacker will send questions like send malicious emails to others, and they will craft jailbreak. They will craft some adversarial suffix such as the red one, or some natural language suffix to these types of malicious questions, and then the large language model will produce disallowed content. And then next content is prompt injection attack, which hijacks the large language model system prompt to execute an attacker's plan. As we can see this figure, normally users want to summarize the article from one website, and malicious attack will hijack this system and output their plans. Next part is hallucination. Model such as this cute question was a victor of the United States presidential election in year 2020, and the ground truth is Joe Biden was the victor, and the hallucination confidently generate fake response like Donald Trump was the victor. And next part is misalignment. Misalignment reflects value gaps. The model reflects value gaps between the model rewards to our human evaluation. And the next part is point attack, which the attack manipulates the training data to embed children behaviors. They can use a specific trigger to let this large language model brains act like the attackers want. And the next part we talk about the privacy concerns, which the large language model will leak some training data or some sensitive information from the users, and that's mainly talk about AI brains. And next part is about the non-brain modules, such as perception paths, such for example in the perception part, such as many adversarial stickers on a stop sign can make a delivery reward speed up instead of a break. And the action, such as supply chain attack or third-party tools or over permission functions that let attacker draft an email and place orders to do something they want. And next part is intrinsic safety, and including the agent-to-agent interaction safeties. First of all, we talk about the memory interaction treats. Agent memory interaction threats, which such as poison retrieval snap and which can steal the future plans of the large language models, and agent to environment risk. Sorry, this part. What is this part? Oh, okay. Agent environment interaction threats, such as the agent interaction with the physical environment. A training bot can create feedback loops and crash markets. That's an example. And also there are some threats in between the agent-to-agent interactions, such as the threats in competitive interactions and cooperative interactions. And the next part, we talk about the super alignment. Normally, standard RLHF cheats helpful versus helpless as one of reward. Well, super alignment introduce a composite object hierarchically, and we briefly talk about super alignment here. And next part, we talk about the safety scan law in AI agents. And maybe I think sorry I think that's it.
Thank you. Cool. So, maybe a few minutes for questions if anyone in the live chat has questions, or does anyone else want to make any comments?
I think that's basically for today.
Okay, cool. Maybe I'll just ask just a few questions. You reviewed a ton of literature. I think around 1,400 citations in the paper. So, what did you learn or find from the research about the information environment for multi-agent coordination, and how can we structure collaborations with human and AI agents? When the amount of information becomes more than any one person might be able to read or make sense of.
So this is for the multi-agent part, right?
Or yeah, for multi-agent, or just for any of the authors in terms of how the paper writing went.
Yeah. Hongzhang, do you want to talk?
Oh, pardon.
Daniel, can you repeat your question?
Yeah. A lot of the multi-agent work focused on the dynamics of the communication, but just from that research and also from writing the paper, what did you find or learn about the environment that the agents interact within?
Yeah, I think it is a newest research topics. We are exploring it. Yeah, but we don't have some specific conclusion. Yeah, we will summarize the latest research paper. Yeah, but
Yeah, from my point of view, I think that so basically we categorize the environments into different types, right? Including the digital environment, the physical environment, and for the digital environment, you have pure text environments, you have virtual 3D environments, or you have GUI. Well, we have a lot of UI agents, right? And a trend is that I think it's related to the agent protocol. Well, if you want to different agents and agent tools can collaborate together. And one important topic is how to develop more unified and fundamentally like universal protocols. So recently we have the MCP from Anthropic. We have the agent-to-agent from Google. So the enabled connection between like inter-agents communications and agent-tool communications, right? So, but there are many others go beyond that. So if you think about, let's say, the Web3 idea, which we hope that everything can be digitalized and connected as a global web. Then in this case, if we want to include more type of resources, more type of entities to work together and share a global context, then the developing more powerful agent and let people in industry, in academia accept that would be a very important thing to do.
Awesome. Well, the paper is a major milestone. I think it could be a textbook or a course. I would have asked what's a good place for somebody who's wanting to learn and get started, but I think that's in many ways what the paper exactly does with providing this kind of a review. So if you have any other comments to make, please feel free. Otherwise, thank you again for joining.
Yeah, thank you. Thank you a lot.
Awesome.
And yeah, that's it.
Great.
Thank you everyone.
Good luck with your research. Till next time. Bye.
Bye.
Thank you. Bye.